So let's start talking about 25-1, our first lecture of the new section, right? So what we have here, and I've underlined V and U. Today we're going to talk about U. Next time we'll talk about V. But remember from a little while ago when I first started talking about electromagnetism in the first place, and I started bringing up all these details, and after we talked about a bunch of particle physics and a bunch of other things you probably don't remember super well, I brought up that Coulomb's law was essentially based off of Newton's law for gravity. That when we were first studying electromagnetism, Coulomb understood that there was kind of a similarity between those two forces, right? It was G m over r squared, and well, that's a fundamental force, and if electricity is supposed to be a fundamental force, then doesn't it make sense that they looked kind of similar? And so we went with that, right? And he chased that idea, and it ended up working out really well. Both forces do indeed look a lot alike. And we had kind of left it at that. We said, yeah, look at that force. And then we kind of forgot everything else that came after that. Right? I'm not talking about electric field. I'm talking about, remember back in 191, when we talked about force and where else we took that idea. Right? We didn't just stop at force. We kept going with that. Today, we keep going with that. So, a bit of review to begin with, though. Remember our good friend conservation of energy. Right? This classic equation that tells us that the kinetic and the potential energy, the total sum of those things into what we call mechanical energy, not thermal energy. That's in an old box of thermodynamics that we don't need to pull out right now. Not thermal energy, just mechanical energy. But mechanical energy can only change if there is a non-conservative force, or not a non-conservative force, a non-conservative work done on our system, object, whatever it is, right? And remember that a non-conservative force is one that is path dependent. So gravity is a path independent force as long as we're, well, all the time, but especially when we're thinking of like what's on Earth and everything else, right? If I lift up drink, I lift it over. This is not product placement, by the way. If Coke would like a sponsorship with me, though, I would be interested. I move it down, I come back here, and I set it back down to its original position off screen. Did the energy of that change between initial and final? No. It didn't matter what path I took around, if I budged it and then budged it back or carried it all the way around the room or anything else like that. The path that I took did not matter. The energy at the end was still the same as when I began, and that is a conservative work, right? Like we are experiencing gravity to be. So right now, we're not super worried about those non-conservative works. Things like friction, for example, that's our big one most of the time. We're just focused on these other two. So let's do a not electromagnetism problem. I've got a ball at some height h above the ground. What's the speed of the ball right before it hits the ground? It's been a little while since we've talked about this, but hopefully this one comes back pretty fast. There's no trick here or anything else. I promise I'm not trying to surprise you guys. Just, it's an old energy conservation problem. I would like to draw some parallels between this one and the next whiteboard problem we have, which is why I'm including it. Right, so we have to think about all of those old ideas that we used to talk about all the time, right? Let's think about like initial versus final and the good stuff like that. In my initial state, I have a bunch of gravitational potential energy. How much gravitational potential energy? Well, whoops, I would like that to be in black for now. That energy, which I use U for that, would be mgh. At the very end, I don't have any more of that potential energy. My height is now 0, but all of the energy that I had before is now being converted into kinetic energy. So at the very end, I'll draw that down here, kinetic energy would be equal to 1/2 mv squared. These two should be equal together. Something like that. And we might have solved this problem some time ago by writing just the very last step of this thing, right? I'm going to include a few steps together here. 2gh, square root of 2gh, and that's it. Right? I'm going to do one thing slightly different. I'm going to leave the m in there for now. So I'll do this in orange. That's the old answer that we would have written down, and that's absolutely correct. What I'm about to write here is not any different than that. But I just want to write it out like this, and I'm going to try and cleverly space things just a little bit. Not by much, but just a little bit. Talk about this. If I break this equation apart piece by piece, I have 2 times a force, mg, times a distance, right? Force times distance is work. Conservative work. It's not the non-conservative work from stuff like friction, but it's conservative work, and that's what makes potential energy. So 2 times force times a distance divided by m, all of that's under square root. Let's come back to this in just a minute. So, pull ourselves out of 191, back into 192. We're talking about constant uniform fields, and what does the potential energy look like in there? Remember that we got work in the first place by basically saying, hey, work is anytime I've got force times distance. Right? We saw it in thermodynamics, dressed up a little bit differently, but it's still the same kind of idea. I need a force, I need a distance. Those two things together give me energy. And in gravity, as we dealt with it in this problem, we had an easy time with it. Because we basically said, hey, look, it's a force that's constant no matter where I'm at, times a distance. And that force is constant over the entire distance and everything is totally fine. There are limitations to that. We should know that there are limitations to that. Using g as 9.8 meters per second squared is only true here on the surface of Earth. Right? If I go up on top of a hill, or if I go down into a basement, 9.8 is not going to change that much. In fact, so little that we have been calling it 9.8 this entire time. However, at a certain point, that height change does become important. Remember that the gravitational force goes as a g m1 m2 over r squared. And so basically what we've been saying is that as long as r doesn't change a lot, as long as it's a really, really tiny change, we stick right around this height that we've got on the surface of Earth, it's not a big deal, and we can ignore the fact that it changes ever so slightly. But if we were to go out to the distance of the moon, for example, that's going to be a little bit more of a significant change. So we're going to stick to this small change or constant force kind of idea for now. And where might we find a constant force when we're talking about the electric force specifically? Well, we've got our good friend, the parallel plate capacitor, or just any infinite plane for that matter. So specifically in this case, what I have is that I can define my electric potential energy as, well, a change of electric potential energy. Let me go ahead and write that. The change of electric potential energy could be something like Q E delta S. Because remember, in all of these points, when we call the ground is zero potential energy, when we're talking about gravity, that's kind of an arbitrary thing, right? What we call zero doesn't really matter. The change is the most important part. In the exact same way, this U naught, whatever we call zero, is kind of arbitrary. It doesn't really matter. The QES is probably the most important part about this. And right now we've drawn this picture out as from the negative plate, but keep in mind this could also be for just a single plate. It doesn't have to be parallel plates. And what happens then? Well, let me get back to that idea in just another slide or two. But for now, just think about it from the negative plate and a positive charge. Because that's kind of what we've got right now. Let's say I have a parallel plate capacitor, and within this parallel plate capacitor, I have a field of 50,000 newtons per coulomb. It's got a 2 millimeter spacing, and I've got a proton that I've taped to the positive plate or something, right? I peel back the tape, the proton flies off towards the negative plate because it really doesn't want to be on the positive plate. What is the speed as it collides into the negative plate? Use that idea of what we just saw in the last slide here. Think about the terms of energy. Okay, let's go ahead and start looking at this one. So let's go ahead and draw this thing out first, right, as is going to be one of our most important tasks for many of these problems. Go and write this out first. So whiteboard, there it goes, took a second. Whiteboard 25-2. Okay, anyways, we draw a picture. 1 plate, 2 plate. Let's pretend like they're kind of looking the same. I've got my positive plate. I've got my tiny little proton. I have my negative plate. And let's go ahead and draw out a lot of these details. So I know I've got a spacing of 2 millimeters between these two. And I'm going to call that S. Why? Because, well, the proton's all the way at the positive plate, right? It's all the way over there already. And while we're here, let's go ahead and draw out the electric field. Right? Just so we remember what direction it's supposed to be going. As I've got a positive charge, I want to get away from the source of positive, go towards the negative, so I'm expecting that my proton is going to end up going this way. Right? So, piece by piece, I want to think about these things. Let's say that I start with a bunch of potential energy and I end with no potential energy and a bunch of kinetic energy. What does that mean? Well, the potential energy that I would start with would be arguably Q times E times S. A force times a distance that I'm going to travel. Right? And we said all of that potential energy is going to be converted into kinetic energy. 1/2 mv squared. Now, I know it's a proton, so I know the mass of the proton, the charge of the proton. They give me the spacing 2 millimeters. I have the electric field as 50,000. Let's go ahead and write these things out while we're at it. So my charge of the proton is 1.6 times 10 to the negative 19th coulombs. Units are important. The electric field is 50,000 newtons per coulomb. The spacing S is 0.002 meters. So the mass of the proton is 1.67 times 10 to the negative 27th kilograms. Let's go ahead and rearrange these two. Let's say that these two need to be equal. What I start with in terms of energy better be what I end with. We're looking for velocity, so let's go ahead and rearrange this thing. And I'm going to go through the exact same steps as before. 2 times the force times the distance. Oh, my pen's doing weird stuff today. Divided by the mass. All of it under a square root. It's the exact same result we just found for the last whiteboard problem. The force looks a little different. It's QE instead of mg, but it's still a force times the distance divided by mass. Multiply it by 2, take a square root. Plug all of this stuff in, we should find something. Where'd that number go on me? I've got it as 1.384 times 10 to the 5th meters per second. But if you're looking in Canvas, I've got it in kilometers per second instead. So 138.4 kilometers per second. I don't know why it's been having so many troubles. Until the exam, like the night before the exam, my office hours have been suspiciously barren this semester. And not to say that I require anyone to come to office hours, but just from what I have seen talking to you guys, I feel like there are a lot of questions that are going unasked. And if I don't see any questions, I can't answer any questions. I try, but like I'm not that good at mind reading yet. So I really do encourage you to use me as a resource in whatever way is comfortable for you, whether that be office hours or emails or scheduling meetings or whatever it is that could help, please do reach out to me. I'm more than happy to answer anything from specific to broad questions, whether it's stuff that we're looking at right now or 2 weeks from now or 2 weeks past from now, right? I'm always happy to answer any sort of questions you guys have or chat about anything that you want to chat about. So I'm just, here's me advertising that if you have questions, please stop by office hours. Please ask me questions. Let's go ahead and keep moving along. So, just as before, we talked about gravitational potential energy when we started by talking classic MGH, right? But as I've just said, if we have a real change of height so that it actually matters, if that difference in r squared, or r in this case, would be significant, say greater than 1%, taking a constant value is no longer a good approximation. It's kind of bad. And we want to avoid bad approximations. We only like to keep the good ones. So it's time at that point to consider a proper definition of that potential energy, right? And when we were talking about this with gravity, we had negative g m1 m2 over r, which was almost identical, right? It's only barely different than the force. There's a negative sign, which let's brush over for the minute. And then it was just r instead of r squared. Because if you remember, we essentially found this definition of the potential energy by integrating that force over a distance. And that distance, being our variable of interest, r, that's how we got to this equation. Now, for a minute, let's think about this negative sign. What's that negative sign telling us? When these objects are as far apart as they could possibly be, when r gets really big, what happens? That value goes to 0. Okay, so no potential energy, no interaction at all when they're very, very far apart. But as I bring them closer together, in gravity's case, that potential energy gets more and more and more negative. But remember, values for potential energy are kind of arbitrary. It's more about the change than anything else. But in doing that, we need to think about what that actually means, that it's a negative value getting more negative as they get closer together. Particles and objects are generally going to trend to being in the lowest energy state in the universe. It's why things don't just randomly glow, right? They want to sit at the lowest energy state at all times by the sign of Q1 and Q2. Get to that in a second here. It's not that they have zero force, right? Because technically, you'll never have the points overlap. It's always counted from the centers of these objects. And I guess this one should be, again, from the centers of the objects here. But it's kind of like this idea that you are standing on Earth right now, right? You are in contact with the ground, but you still feel the gravitational pull because the centers of those two masses are still separated by that distance. But generally speaking, it's favorable for the objects to be closer together, in terms of gravity at least, right? That's where everything wants to be. It's close together. That's what gravity wants. That's the lowest possible energy state, right? It's a lot easier to drop a book than it is to pick it up off the ground, because gravity would much prefer to have the book on the ground. So when we think about the electric force, we almost have a one-to-one translation, right? We have our constant K instead of G. We've got the two quantities, Q1 and Q2. We've got 1 over R, right, instead of R squared. Everything looks fine, except mass was always a positive value. Charge has a little bit more variety to it. And also, if we remember that difference in force, gravity was always attractive, whereas the electric force can be attractive or repulsive. So it would stand to reason that the potential energy could also change sign in the exact same way, right? Because if I put two positive charges very close together, Well, certainly they don't want to be there, right? They are going to repel each other and they're going to try and fly off and to be on opposite ends of the universe. And in doing so, they went from a high potential energy down to 0. Whereas if I had a positive and negative, they'll do what they can to come back together. I went from 0 potential energy to a negative potential energy, and that lower energy state is what the particles strive for, right? It's falling for them. The negative charge, the positive charge is falling towards the negative charge. That's what it's trying to do. The positive charges are trying to get away from each other, right? It's kind of like falling in reverse almost in a strange kind of wraparound way. But that's why this one doesn't have a negative sign in front of it, because if it's positive, positive, then they're going to be more potential energy closer together, less potential energy away. If it's positive and negative, then they're going to have smaller potential energy, or I guess more negative potential energy closer together. So that's how these things are going to trend. Now, that works great for two particles. And one thing that we didn't really consider in gravity is what happens when you have more than two particles. I'm gonna move myself back up for a little bit. Well, luckily for us, and let me delete these things for now. Let me write those out organically in a second here. Finding the potential energy of an ensemble of charges like this, or a group of charges like this, is actually pretty easy. It's not so bad. All that we need to do is we need to think about each individual pair of particles and the potential energy between those. So if I wanted to know the potential energy of all of these charges together, I would take the grouping 1 and 2, and 1 and 3, and 1 and 4. And then also 1 and 5. But I need distinct pairs, so let's go ahead and write these out. So let's write out our pairs. I've got 1 and 2, I've got 1 and 3, I've got 1 and 4, got 1 and 5. Now I could do the exact same thing for 2, but if I start at 2 and 1, I've already counted that pair. I've already done 1 and 2, so I don't need to do 2 and 1 again. I'm going to start 2 and 3. And then 2 and 4, 2 and 5. Same deal for 3. I don't need to do 3 and 2. I don't need to do 3 and 1. Both of those have already been counted. So I'm going to do 3 and 4, 3 and 5, and then finally 4 and 5. Somebody brought up in the last lecture that it's kind of like how you consider a factorial, and that's how I often think about it, right? I'm going kind of down like a staircase like this to get all these different values. But that's what we mean when we say sum up all of the distinct pairs. That means if you've already counted 1 and 2, don't count 2 and 1, because it's the same pair, which mathematically sometimes is easier said than done. But in a case like this, when we're dealing with, let's say, a countable number, right? 5 or less or something like that, this is the easiest way to do it. So let's try this out. We've got 3 charges here, which when you're calculating everything out, you should see 3 distinct pairs or 3 terms in your total potential energy. What is the total potential energy of the group of charges as shown in this picture? All right, let's go ahead and take a look at this. So the first thing I'm going to do here is I'm just going to circle all 3 pairs that I'm expecting to see. So here's pair 1 in red. And these are all going to be not fantastic. The first one was going to be the best. There's loop 2. And then pair 3 is going to be something like that. Right? And now my picture's a mess, but I've got all 3 of my pairs counted. So I'm going to say my total potential energy is equal to the sum of every single pair that's distinct. So I'll just write that as like U, I, J for 1, 2, 2, 3, and 3, 1. But now I'm going to write these out color-coded. So for my red pair, what I'm expecting to see here are my top 2. So this is going to be K times 2 nanocoulombs times 3 nanocoulombs over 0.03. Blue pair, K times 2 nanocoulombs times 3 nanocoulombs over 0.04. My green pair, This is a 3, 4, 5 triangle, right? Which Pythagorean theorem will get you there just in the exact same way. But if you see that, you can jump on it. So 3 and 3 this time around over 0.05. Now, I'm going to show you how I might try to speed up my calculations and avoid any spots that I might get myself a little bit mixed up on my calculator. In every single one of these, I've got K times 3 nanocoulombs times some other stuff. Let me pull out the K and the 3 nanocoulombs. And even more than that, let's think about this. K is 8.99 times 10 to the positive ninth. Nanocoulombs is whatever times 10 to the negative ninth. Those 10 to the ninths cancel out. I could leave myself with 8.99 times 3. 10 to the positive ninth, 10 to the negative ninth, they've canceled out. That's all I'm left with is those two numbers. That's one way to help speed this up. Now I'm going to multiply this by what's left. So I have 2 over 0.03 plus 2 over 0.04 plus 3 over 0.05. And I haven't forgotten that the second term was also nanocoulombs, because what I'm going to do here at the very end is multiply all of this by my 10 to the negative ninth. So the first nanocoulombs term got killed off by my Coulomb constant K. My second one, I've just left it on the back end of the equation here. And that just simplifies the whole thing a little bit more, makes it easier for me to type in, and I'm all about going fast in these problems. So, sum all that stuff up together. What should we find? Something like 4.765 times 10 to the negative sixth joules. Or as I've got it written in Canvas, 4.765 microjoules. So, here's a fun one, right? This requires a bit of cleverness to solve this thing properly. I have 4 1-gram spheres arranged in a square like this. Each of these has a 10 nanocoulomb charge. Somehow they're all being held in place. And then suddenly, whatever gatekeeping I'm doing on these things, I pull it off and they're all allowed to fly away at once. So all 4 of them move. What is the speed of each sphere once they are very far away from each other? There's a clever trick you can use with this problem to make it much easier than you might otherwise have to do. But you've got to think about where the energy starts, where the energy ends up, and how it gets distributed among all the parts. All right, so let's start to take a look here. Had some good discussion going on in chat, so more than happy to see that. But let's go ahead and move this thing on over so we can take advantage of the fact that we have a drawing program instead of using paper. And I should probably section this off, shouldn't I? Make this a little bit easier, so we'll split that off, wrap that around, there we go. And this is whiteboard 25-4. So, before I get all the way into this, let me think about this piece by piece. Before release, or at the instant of release, I can argue there's a kind of symmetry to this, isn't there? If I draw this line, and I draw this line, can we agree that each quadrant looks identical? Right? If I spun this by 90 degrees in either direction, I would never be able to tell the difference. Everything would behave exactly the same as far as I could tell. Think about the forces acting on each of these particles. I'm going to experience a net force that looks something like that. and a net force that looks something like that, and a net force that looks something like that, and a net force that looks something like that. I don't want to do this with kinematics. I could, but I really don't want to, because I have a non-constant distance between all of these particles, which means I would have a bunch of terms that are non-constant playing into my acceleration, and we have a bunch of kinematic equations for a constant acceleration, but for a non-constant acceleration, it requires a lot more calculus. And we ran into this problem last semester, right? We basically said, hey, what do you do once you don't have a constant acceleration anymore? How can you still handle this problem and solve it, right, in any sort of reasonable way without spending days working on the same problem? Well, we go to energy instead. So let me think about this. This ensemble, whatever it is that goes into this, has a total potential energy when we start, but no kinetic energy. So let's say initial is U total. I'll just leave that there for now. And kinetic energy, capital K, is equal to 0. Final. When they get infinitely far away from each other, anything over infinity is 0, right? Or approaching 0. So we're saying that at the very end, my potential energy is 0. All of the energy has gone into kinetic energy. But it is not just the kinetic energy of one single ball. It's the kinetic energy of all 4. Again, think about that symmetry argument that I made here, right? Every quadrant looks identical. So I could argue that if I had rotated this by 90 degrees, then the particle in my top left now should have the exact same kinetic energy at the end of this as had been before I rotated. So total kinetic energy is going to be 4 times 1/2 mv squared, because there are 4 spheres all taking a piece of that initial energy. Okay, now we've got a couple different things to worry about. We're looking for speed. So our final energy, 4 times 1/2 mv squared, leave that alone for now. We want to find that. We need to figure out what U total is first. And so what I'm going to do is I'm going to first highlight all of my pairs. I've got this one and this pair, and that was not a good pair, and this one and this one. And then I've got this one and this one. And that's a mess to look at. So you know it's a little bit easier than that? Let me look at these top 2. 10 nanocoulombs, 10 nanocoulombs, separated by 1 centimeter. Do I see that anywhere else in this picture? While that's technically a real question, it's mostly rhetorical because, of course, it's a square, and they're all the same charges on each corner of the square. So let me save myself some work, and let me just say that U total is equal to, what's that potential energy? K times 10 nanocoulombs squared over 0.01. There's 4 of those pairs. Then I have my 2 diagonal pairs. I've got a triangle made out of this. This centerpiece is going to be 1.41 centimeters, or square root of 2 centimeters. And I've got 2 diagonals. So what's that potential? K times 10 nanocoulombs squared over 0.0141. 2 of those. Make my life a little bit easier, right? And now again, I'm going to try and, these things are a little bit long if I try and do these things full on proper, I guess. So I try and save myself some work here. Let me just go ahead and pull this thing out. I can do something like that to make the calculation a little bit easier. And what I should find is, I wrote this down on this slide, but I don't have it somewhere else. Total potential energy, cover that up for now, 4.845 times 10 to the negative 4th. So not a lot of energy, but a little bit. So now I've got that total energy. I need to set that equal to my ending kinetic energy. So U total is going to be equal to 4 times 1/2 mv squared. U total is a number for me at this point. I'm not going to worry about anything else on that one. V is equal to the square root 2U over M. Mass, remember, is 1 gram. We just found that potential energy. What we should find at the very end for our speed is 0.4933 meters per second. Just like that. I love this problem. I think it's a little bit clever because, like, realistically, you've got to really think about, you know, there's still a symmetry argument that has to be made, right? That's not something that we can really avoid here. It's much easier if you consider the symmetry of the problem and take advantage of that symmetry. It's not just for electric fields. We can still use it here. Shouldn't the 2 be on bottom? Yes. Yeah, probably should. Oh, now some purple. Oh, no. Thank you for catching that. One more, and this one's going to be a little bit more tricky. I have 2 metal spheres with masses 2 grams and 4 grams. They're tied together by a 5 centimeter long massless string, right? So let's say center to center, 5 centimeters. Everything starts at rest, but the string is taut between them. If each of these metal spheres is charged with 2,000 nanocoulombs, what is the energy? What is the tension? And finally, if I were to cut that string, what is the maximum speed of each ball? And I want to give you a warning about part C here. The kinetic energy is not necessarily evenly distributed between each ball. You need to think about that one a little bit. What else you might be able to use to help with that part of the problem? Are we ready? Let's go ahead and start on this thing. So, step 1, as always, draw out a picture. I'll box this one in later. So whiteboard 25-5. I have a small sphere. I have a bigger sphere. Clearly, these are very well drawn to scale. They're both metal. Let's go ahead and negate that. Bam, now we know they're metal. I've got M1 and Q on this one, M2 and the same Q on this one, right? No surprises there. So part A is asking us to find the energy of this system. There is no kinetic energy because both of these things are at rest. So all of the energy is electric potential energy. There is only one pair that we actually have here, so this is going to be K. Q1, Q2 over R. And R, we are told, is 5 centimeters. M doesn't have that many humps. It's just 2. So, plug in all my values. Make sure that we are always in standard units, just for safety. And what I should find at the very end is something like 0.72 for my total energy. Just like that. Now, part 2, we're asked to find the tension in the rope that's holding these two together. So, okay, that sounds like a job for a free body diagram. So if I draw out, and let me think about this for a second. If I was thinking about the rope that's connecting both of these things, remember that the tension is the same throughout the rope, right? The rope pulls with the same tension on every spot that the rope is connected to. So if we solve out for the net force on one ball, we've got the tension in both ends, right? We only need to focus on one of these. And that's what I'm going to do. So I'm going to say, okay, let me look at the big one here because it's a little bit closer to the edge. I have an electric force that is repulsive going out like this, F of E. And then I have tension, making sure that I actually don't fly off. Like that. All in all, when everything is done, I should have 0 net force. Electric force pushes to the right. Tension pushes to the left. Or pulls to the left, I guess. It's a rope. I don't know. But anyways, this is one that we could actually have done with just our chapter 22 stuff, right? K, Q1, Q2 over R squared minus T is equal to 0. Rearrange it. You know, it's a slick trick here to make this even faster if I really wanted to. I already solved out for K, Q1, Q2 over R. Divide that value by R one more time. T should be equal to 14 point, shoot, what was the actual decimal? 14.38 newtons. It's a slick way to speed up that calculation a little bit, if you recognize some of the similarities between terms like this. So I always like to do things symbolically, even if I am going to plug in numbers. Okay, and finally, here's the tricky one. So I gave you the hint earlier that the kinetic energy is not necessarily divvied up equally between these two spheres. And now I can confirm that it's definitely not. Let's write this out. Total energy, or let's do change. Let's do total energy. So when we started, we had a bunch of potential energy, U. When we ended, assuming that we flew out to infinity, all we had left was kinetic energy, and we had the kinetic energy of each sphere. So that's 1/2 m1 v1 squared plus 1/2 m2 v2 squared. I don't know how V1 and V2 relate. I don't know if they do. Is there a simple way that they relate together? It's not clear to me. Right? There's nothing in this that says how these two values are going to be, or how that energy is going to be divvied up between these two. So I need to think, okay, energy conservation got me maybe part of the way there, right? I have an equation, but I have two unknowns. Was there any other quantity that was conserved as these two flew away from each other? I will end up using the ratios of their masses, but I would like to know how I should get there without a guess and check method. There's a surefire way here. As much as I'd love guess and check, momentum is the answer. Think about it like this. When we started, there was 0 momentum. Was there any external force acting on either of these? If not, then the momentum of my system, after everything is said and done, should still be 0. As long as there's no external force, momentum is conserved. Momentum started 0. It better in there too. To the right, I have M2V2. To the left, I have M1V1. That is to say, let me rearrange this thing and let me say V2 is equal to, if I move that around, this should be M1 over M2 times V1. So there is a ratio of the masses, but We just need to be sure that we know how to get there. So now that I know that, let me take my energy equation back down, because really the trick to this was I see V1, V2, two unknowns. I go to my momentum equation, V1, V2, two unknowns, two equations. It's a solvable system. So solve out for V2. Let's go back to my energy equation. Let's plug it in. What do we get? And I'm leaving this as U because this is a number for me at this point, right? I don't need to do anything else to that. So that total energy must be equal to 1/2 m1 v1 squared plus, now this is where it gets a little bit nasty, m1 squared over m2 squared v1 squared times m2. Okay, it's a little bit crazy, but not to worry. I can cross off one of these. So let's do this in orange. Cross out that with the squared. So I've got m1 squared over m2. And let me do a quick check. Does this make sense? My kinetic energy term was kilogram times meters per second times meters per second. If I have m1 squared over m2, that's kilogram times kilogram divided by kilogram. 2 of the kilograms cancel out. I've still got my kilogram times v squared. My values work out. Dimensional analysis has told me that my units are at least safe. Doesn't mean I didn't miss a constant somewhere, but at the very least, my units are safe, and if something was wrong there, that was a red flag. So, passes that check. Let's go ahead and keep doing this thing. Now that I've got this, v1 squared is in both terms. There's a 1/2 in both terms. I'm going to rearrange a few things here. Let's pull out the v1. Let's have, so 2u over m1 plus m1 squared over m2 is equal to v1 squared. Better yet, let's throw a square root over this whole thing. When we do that, we should find at the very end some v1 that looks like, I had the number here somewhere. For v1, it should be 21.9 meters per second. And I'll go ahead and write my conservation of momentum. Just to have it. When we go back up to the V2 equation, we plug in V1. It's really just half of V1, right? So 10.95. Whoops, I should probably have done the V2 is equal to 10.95 meters per second. And there we are. I love these ones, right? Because all of this cumulative physics knowledge coming back from what you thought was the grave, but was just a temporary resting place before all of these things are back again, right? And it's October right now, so I'll even go as far to say back again to haunt us. Right, but it's a lot of fun. We get to tie all of this old knowledge in together. This problem has, like, what, 7 different chapters worth of material all written into it at once? That's kind of neat. It's a fun time. But it's proof to the concept when I keep telling you that physics is cumulative. That old information is still useful. Let's go ahead and close out the lecture. So, our good friend the dipole is back, right? It's kind of like how we do with every single chapter. At the very end of the first or second lecture of the chapter, I talk about dipoles, and we briefly sprinkle in some details, and then we go back off to point charges again. But let's go ahead and get our brief little experience of dipoles for the day. Dipoles experience torque. Yes, of course, they don't want to be not aligned with the electric field. We've seen that a couple times at this point. But they also will experience a potential energy, right? Because think about this. If they're in a uniform field like this, and this is a uniform field specific thing, but if they're in a uniform field like this, The positive charge, just like way back up here, wants to go towards wherever the negative stuff is, right? The negative charge wants to go towards wherever the positive stuff is. So if they're anywhere other than aligned with the electric field, they don't really want to be there, right? They want to be aligned with the electric field. And this is actually how we get essentially a pendulum out of our dipoles, right? When we were talking about way back to that whiteboard problem from a while ago, when a dipole would swing about back and forth, pivot on its axis, right? That's exactly the same thing that would happen here. And remember that we talked about pendulums in the sense of, okay, first you talk about forces, but then you think about this thing in terms of potential and kinetic energy. Dipoles do the exact same thing. So we do have a little bit of a standard in this one, and this is kind of an arbitrary value again. We're going to call, when the dipole is completely perpendicular to the electric field, we're going to call that potential energy is equal to 0. If it's turned around, so if I kept turning this thing clockwise and I made the positive charge go all the way over here, and the negative charge go all the way over here, so it's completely misaligned or backwards against the field, that is going to be my highest possible potential energy, right? It really doesn't want to be there. But if I allow this thing to actually rotate in the other direction so that it is aligned, that's going to be my negative potential energy. And again, it's a bunch of arbitrary values. The change is the most important thing. But that's where we're setting that arbitrary value. So in doing that, though, the math gets a little bit easier to deal with, because what we can say then is that, remember when we were talking about torque, how we had P cross E, and the units of that are technically Newton meters. Newton meter, it turns out, is the exact same thing that makes a joule, right? We came into this discussion last semester as well, how torque and energy technically share units, but not really. It's not a value that can transfer over back and forth between those, because remember that energy is a scalar value, torque is a vector value. But it should be then no surprise if they share units that energy looks, well, a whole heck of a lot like torque does. But instead of a cross product, it's a dot product. It's got a negative sign that says when it's aligned, that's the lowest possible energy. That's where it wants to be. And we get an equation like this. Negative PE cosine of phi. So, let's go back to our old pendulum questions. Let's say I have a dipole and it's made of two 1 gram spheres, and each sphere has, it's plus minus 2 nanocoulombs on the end of a 10 centimeter massless rigid rod. So it's not going to bend or anything else. It's going to spin like we expect the dipole to. The dipole rotates frictionless, pivot at its center, no energy lost, no non-conservative forces or anything else like that. And the electric field is a constant, uniform 1,000 newtons per coulomb. What is the angular speed of this dipole when it's perfectly aligned with the electric field? All right, let's go ahead and start taking a look at this thing. So I'm going to steal this picture, make it a little bit easier to see, and I'll go ahead and draw all over this thing. Let's go ahead and take that up there. So, as I was kind of saying before, when we're thinking about this thing right now, when it starts, I have a potential energy of 0. And then I have a kinetic energy, because this thing starts from rest, I have a kinetic energy also of 0. Which maybe this raises some red flags for you guys, and that's okay if it does, but let's talk ourselves through this. We are interested in the point once this has rotated down and it is aligned with the electric field, right? So those would be that's where those two charges would be going. What does that mean? Well, in my final state, I would then be expecting to see that my total potential energy would be negative PE. Cosine of theta is cosine of 0, which is just 1, right? And I'm expecting to see that negative value. That's my lowest energy state. So we've got a little bit of wiggle room, right? It should be equal to 0, so if we see a negative sign, okay, our kinetic energy can be positive, all is well in the world. However, we've got one last thing to deal with here, and it's the fact that we don't have any translational kinetic energy. We have rotational kinetic energy. Just a little bit different, remember. But rotational kinetic energy is 1/2 I omega squared. Okay, well, let's think about this thing piece by piece then. The potential energy, I remember P, that's just the dipole moment, so that should be Q times S and then times E from B4. And both of those are values that I actually have, right? S is my 10 centimeters, Q is my 2 nanocoulombs, and I'm all set with that. Omega is the thing that I'm after. So I just need to figure out what I is, and I should be ready to solve this problem. It's been a little while, but you might remember that anytime we're talking about the moment of inertia from a point mass, it goes as not 1/2, just mr squared. So if I'm looking at what we've got here, S is half of this, right? This distance right here is S over 2. This distance right here is S over 2. So if I'm searching for this thing for real, then I would have M times S over 2 squared. And then I've got one on top and one on bottom. So there's 2 of them. Simplify that a little bit more. MS squared over 2. Perfect. We have our moment of inertia. We're looking for omega. We've got Q, S, and E. We're ready to solve this thing. So let's put all this stuff together. 0 is equal to 1/2 I omega squared minus Q, S, E. Plug in what I just found for I. Let me divide by S. That'll make this a little bit easier. So cross out that one and that one. And then I'm going to move the QE to the other side and combine some things. QE is equal to MS over 4 omega squared. Omega is equal to 4 QE over MS. Square root of the whole thing. And that's it. What we should find is 0.283 radians per second as our final answer. And that's it.